Dear Ayla, dear audience, thank you for inviting us. It is a real pleasure for us to be at the CCA in San Francisco. It's the first time that we're here, and we would like to share a couple of projects and thoughts behind the project, and especially also research which we conduct at the ETH Zurich, and our motivation why we do this research and why we think this research might prove to be relevant for architecture. We would like to start by jumping in a very old project of ours, an office project which we did in 2003. It's called M-Table. So M-Table is, as Matthias said, a project that we did the office before we got the position at ETH. Back in 2002 we used to call such project research. Nowadays we would speak about recherche, something more lightweight somehow, but we're still showing this project because somehow it illustrates in a very clear and straight way a couple of things that are important to us. M-Table was conceived as a project, was basically a software running on a mobile phone, first generation mobile phone with a complete OS operating system. So the first phone you could program and that was able to run software. Now M-Table, this little software, I have a movie showing it here, basically with the software you can design a table. You have the surface of a table, you can choose parameters like length and width. Then you can place up to seven points on the surface and put pressure. By pushing on the little joystick, put pressure on this point, and by putting pressure you deform the surface. If the surface is deformed enough, the lower surface cuts the upper surface of the table, and you have an intersection and you get holes. Here you see the whole process. When the customer playing around with the software is satisfied with his design, he sends the design to the server, and he sends this data, a very simple set of data identifying the whole shape. So it's human readable. It contains the color, the authorship, and so the extension of the table and the position of this point. So it's a very simple code transmitted here. If you know the algorithm, the system behind the whole thing, with this minimal amount of data, you can generate the high-resolution software, so the geometry behind. This geometry can be sent directly to a CNC mill, and the shape that was designed on a very low resolution, very simple, very primitive, this CAD software somehow is then transformed into real material in the highest possible resolution. So here I have a couple of images of sold tables. So this project was not just a hypothesis. We did it, and we wanted to test what happens if you do something like this. Our interest in the project, and in order to come back to the beginning, the reason why we are still showing it is following. M-Table illustrates in a very direct way what happens if you connect data, so numbers, parameters, with material without any interface in between. M-Table, of course, is I would say now an ironic project because it's pushing the whole issue of parametric design to its limits. So as a designer, we do not conceive form anymore. We really leave the decisions on shape to the customer, a customer that is not educated in any way in design issues. We just define the system. So we formalize rules that allow, you see from those examples, to produce or to output very complex, very interesting, very appealing products that at the same time are questioning the function of the table itself. This is the ironic component of the M-Table project. The table with holes somehow is a silly thing because it questions the function itself. So giving this in the hand of an uneducated person raises a lot of questions that will be addressed in the project. The more architectural project we will show later on. Here another build example. And I close this project with this image that is very interesting because it shows this is a little sample out of not a build table, because in the end just 10 of them were built. It was an expensive high-end design product, but a lot of people engaged with the possibility of buying or designing a table, and so left her traces on our system. We're collecting this design tryouts, and we show here a little collection of them. And what this image shows is that even though every single table here design is completely different, some have no holes, some have more holes. If you look at them in detail, some of them are very, very nice, others are ugly. What is common to all of them is that, or what the picture shows in an impressive way, is that the design intention, our design intention as authors of this project, is still very strong. So as a conclusion, I could say when we did this project, we proved to ourselves that to engage with the design of rules of systems instead of being obsessed by form is not a risk for our profession. Because here, even though every single customer has the impression to have an enormous amount of freedom, he cannot step out of the kind of constraints, even formal constraints, very strong formal constraints we give to the design. So I'd like to quickly introduce the topic of the lecture, which is also the title of the book, which Ayla already mentioned, Different Materiality in Architecture. Why do we talk of different materiality? To us, this is a kind of intermediate, maybe, naming of something which we see happening and which we believe it might become interesting for architects and architecture. On the one hand, when we produce designs today, if we, even by drawing a simple line in a CAD software, we produce data. So automatically architects are producers of digital kind of artifacts, which are then being either human read and interpreted or directly with digital fabrication machine read. So you know all this. But architecture has also a material culture. So it's basically the culture of construction, and well, especially at a school like ETH, this is also a heavy focus on how architecture is conceived and where architecture can actually derive certain contents or concepts for its own expression and performance from. So the fundamental question for us, or maybe the problem when we actually also started our office, was, well, how do we bring those two things together? Both Fabio and I could program when we started our office, and on the one hand. On the other hand, we have gone through, let's say, rather classical architectural education. Now, if you look at those two separate worlds, it's not very convincing that you start going into professional practice and you have like kind of these two potentially interesting and kind of powerful ways of or tools of conceiving actually two different things. One is making a building, the other is making a computer program which does something on its own. So the linking for us was very fundamental to actually find this linking. Now, where did we find it? We actually find it in the construction process itself and linking it directly to the fact of programming. Because if you program a computer, you do nothing else than setting up sets of rules, kind of sequences, steps, which are executed one after the other by the computer. So you have to conceptually think about what the computer does and what are the conditions under which the computer does those steps. Now, if you think of making a building, literally building up a building, you have similar, I would not say they're equal, but you have basically similar steps. You're basically building up a building from its foundation to kind of the structure, to the cladding, ceilings, and so on. So we will start to get interested in this question if, on a very basic level, we start to merge the concepts of, let's say, architecture and computer programming, and start to look at this in a more synthetic way. Now, for us, this kind of the term digital materiality describes this potential shift when we say material is not just the mere material anymore now that we work with computers, but it's actually the material which is kind of infused with the characteristics of digital logic, which is directly brought into the build-up process of material elements. So the material itself is transformed. Now, we think this might be relevant for architecture because each time new architectural building materials have come on the market or were developed or were invented, let's say, for example, reinforced concrete or glass or so on, there was actually a very heavy impact on how architecture would express itself, how it would change, and what would make sense as architectural solution. So we think if we take kind of what is happening in the digital domain as relevant for architecture, we don't think it is just a tool these are just the tools which are helping us to kind of solve more complex issues. But if we think there are certain concepts within this digital culture that it can actually enrich the architectural culture and find a new balance or make new meanings in between, and thus become kind of a new conceptually new building material for architecture. Now, this is the hope. I wouldn't claim that we've proved that this will really be happening, but we're very interested in what these developments could be. Now, to start, I would quickly show 3 projects which are kind of a step before this kind of material, kind of the physical materiality of architecture is really being infused by digital information, but which is the most direct way of how material and information meet. It's actually kind of digital building materials. I'm talking here of the subject of light. Here you see a couple of LED lights of the Christmas illumination in Zurich. And we did a couple of projects and just kind of quickly browsed through them to give you an idea, which work with this kind of material of light. Light is very nice because you actually, nowadays you can control it over time. So suddenly the design of such an installation like you see here, this is an installation, a floor installation on a street crossing, not only becomes kind of a static product, so one shape, but it also becomes a design in time. So the concept is actually how do you shift, in this case, the colors, because this is a polychromous installation, over time. We can I'll show you another project. This is a city park in Uster, where we designed these lamps, which you see here, these park lamps. What is special with these park lamps is that they fill up with light, or can empty themselves with light. You're going to see it in the video just coming, depending on where the observers are. So on the one hand, we design an object, this artifact, this lamp, which is merging between a candelabra light and a kind of floor light. And on the other hand, we design the concept of how this lamp is going to behave in time. So this is the programming aspect of the designer's program. This installation here at the open lamp. This is the picture within the lamp, this is the video recording. So what you see is the person is walking by the lamp. The light starts to throw up in this lamp, and it starts to fill with light. So if this part is empty, you just have a very low shimmering kind of dot of light. And if people are walking through the park, and start to fill with light. This means the park is, can be used with light 24 hours a day, but the energy consumption is very low. Kind of in a dim mode, with no rain. I'll show you a latest project of these light installations. Light can be very large scale also. This installation is 1.1 kilometer long, and it's a kind of Bahnhofstrasse in Zurich, the most prestigious shopping street in Zurich, where we won the competition for Christmas lighting. And this is the installation. So it actually spans the middle of the streetscape and articulates the bends of this urban situation. It's composed out of 275 lighting elements, which, through the fact that you move within the streetscape, form this ribbon of light. So if you look at this installation from sideways, the elements are spaced very widely from each other, but because you always move within the streetscape, you have this ribbon. Now, of course, this is one part of the design, these physical artifacts, and then there is the software part of design. Here you see the software which actually generates the atmosphere. It's an atmospheric pattern on this ribbon of light. It's called a Christmas generator. Software is programmed in our office, and it generates patterns which are roughly like those. You must imagine the pattern you see on the bottom stretched over this 1.1 kilometer. I'm not going to go into the details, a lot of details about these projects, but just to give you an idea. So there's kind of these two parts of design. I would like to quickly share with you how this looks like in motion. This is a small video from the opening. Okay. Now, after those light projects that illustrate the side of the control of the logic and of design processes in time, we move directly to the hard material, to the architectural scale. This is EFAB at ETH. This is our say unit. We teach there. This is composed first of all by people. This is our team, and by a machine. This is our robot. Now, normally we would not put special emphasis on a machine. When we got this position, we didn't know that we would buy or set up such a lab. We were used to, as I've seen in this M-table project or in other projects we haven't shown here, we're used to go out in the industry and to look for possibilities for machines available out there, and then understand the logic of the machines and find ways to realize our design intent. Here we were asked by the president of the school very quickly when we started to talk about the position, how this could work. They asked us which machine we would like to buy, and of course this for a school in general, but for ETH in special as a large technical school. Is an important question. So in the beginning, you get your money, so you have to make your decision. And we were not prepared to this question. So we started to look at what possibilities we would have, and very soon we were attracted by this special machine called industrial robot. This is the orange part. It gives you an idea of the scale. The arm is about 3 meters high, so it can reach by moving on this rail here. It can reach a space of 7 by 3 by 3 meters. So it addresses a architectural real scale. So what can be done here can be transported. So it's classical prefabrication. And what is special in this machine, and what still is very interesting to us on a conceptual level, is that this machine is completely generic. So when it comes, if you buy it, it's just the orange part that is delivered. It's an arm. It has no tool. It's just the possibility of moving in space and performing somehow some kind of operations. And if you compare it with other machines, so-called specialized machines, you can say a laser cutter is a specialized machine, a CNC mill is a specialized machine. There is one main difference. First of all, the price. And we think this is a very, very important issue, the price, the economics around the machine or production process in architecture, because in architecture we always speak, even if you do not operate in social housing, architecture is always about big scale and small budget. So if you do not produce parts for airplanes and so on, it really matters how much production costs you have for, I don't know, a certain amount of material. This machine is extremely cheap. This is the interesting thing. Even though this machine is very advanced, robust, perfectly engineered, this machine is cheap for two reasons. Because it's an industry standard since, I would say, it was invented in the 50s, but since 30 years now it's an industry standard. Since the beginning of the 90s, you have maybe 5, 6, 7 big companies producing them. They are selling thousands of such machines to the automotive industry. They changed completely the paradigm there, and this leads to the fact that for the engineering cost of this complex machine can be divided on millions of pieces sold. It's like cars. It's the same paradigm. A CNC mill, even a good one, maybe they have a couple of thousands of pieces sold in 5 years. Then they have to change everything. So there is a lot of engineering costs and effort that you're paying. The most interesting thing is the difference to the CNC mill is that the machine is, as I said, generic. So not having a tool, it does not influence the way you use it, for a simple reason that you cannot use it in the beginning. If you get a mill, you can mill. So you have a scope. There is a precise process that comes, and a set of course, images and possibilities that influence your work and your approach in a very strong way. Here, first of all, when it comes, you have to think about what you will do. That's the first step. And the second step, you have to engineer, to develop, to design, not just the data part. So what do I, or how do I move around in space? So what do I mill? But how? So the tool, the physical counterpart to the data, is part of the design process. When we got this machine in 2005, it came without any tool, of course. We knew that we would like to, in the middle and long term, to go into additive fabrication, to use this arm as a tool to move around material, to stack material, to add material. But because we got it just a couple of days before our first studio had to start, we decided to work with perforations. Because the simplest thing you can do if you have an arm is to put a drill on the arm and have a machine, a setup like this, that is basically just able to do what everybody knows from personal experience, to drill holes. What is, as a starting hypothesis, extremely simple, banal. Of course, we were interested in perforations. It was a topic that interested us, but here it was, I mean, if you compare the simplicity of the operation with the holes of this M-table project, where you have a milled shape going to zero thickness on the border, those here are very let's say rough things. But what was interesting to us and to the studio was the issue of large numbers. It was always also showing our approach on the machine and allowed us to test its potential. A machine for us, this industrial robot, is not or does not, even though the term and the machine evokes a lot of thoughts about rationalization, about automation, about making things faster and cheaper and more efficient, because it comes out of this industrial logic of the last century. What interested us was just the ability of a machine without any intelligence, because this is another potential misunderstanding. If you see, or better, if you heard the term robot, you think about intelligence. You think the robot acting, the robot seeing something, maybe thinking. And in the industrial robot, this is completely false. The industrial robot is just 6 motors that are controlled by data. They are just fast and precise, that's it. So what's the interesting difference to the human, or where could we potentially exploit this strength? It's on the issue of large numbers. And it's the same reason why programming or software is interesting to architects. It's when it comes to, and here you see it, the setup of the first of this studio was, we have a architectural abstract body, and we have a drill, just 1 diameter, and we have 2,000 holes. Now 2,000 is a problematic number, because if you are used to design doesn't matter by hand or with software, you know that 2,000 elements you cannot deal with 2,000 elements. So either you have a very simple, straightforward logic, a grid, for example. So you do an array, 2-dimension, 3-dimension, then you can handle it. If you want to compose or to apply a more sophisticated or complex logic, everybody that has designed a facade or put windows on a facade knows if I have 5, 10, 20 maybe, I can, if I spend a lot of time through iterations, organize them. If I have 500 windows, I have to use grid. A very simple logic I can deal with as a human. Now, on the programming side, if you have complex software, you can script. This is the paradigm shift happening right now. Then you can control larger numbers of data. On the physical side, you have the same kind of problem. If you have 10 holes, you can drill them by hand. Because worst case, it takes you half an hour per hole to set up your, to take measure, to build tools that will help you and so on. If you have 2,000 of them, it's helpless. Now the robot has the strength that it doesn't absolutely care about where those holes are. So the workflow is always the same, takes the same amount of time. See here, those were was the first part of the problem. Where do we want to perforate this volume? To organize the data in two dimensions. And the second thing is, it makes the exercise or the output then very interesting on a spatial level, is the fact that the robot doesn't care about where the holes are, but it doesn't care about the angle too. What would be really complex by hand has the same simplicity. On the other hand, this means or meant in this exercise, if I have this freedom, taking 2,000 holes, putting them somewhere, and giving them not just information about the position, but also an angle, is how do I design this? How do I produce this data? So this was the whole thing. This was a result of a group of students. A very simple logic of distributing these holes. We show it normally because it illustrates how such a simple process, physical process, that everybody would say no problem, take a drill and make a couple of holes, can have what the consequences are. So this is the same cube. And first one, it's lit on the outside, and here you have light on the inside. And you see that just by two operations, logical steps. The first is to group holes around a corner, and the second step is, this becomes visible here, to give this whole group the same direction, so all those holes around this corner are looking at one point in space. This creates here on the surface a further new size or geometry on this very simple volume that does not exist in geometry, that it is more present than the other ones. Plus, if you reverse the whole thing and you put you in the inside, you will have one position in space where, because of this large amount of perforations, the geometry will disappear, because it will not have any depth anymore, because we are exactly in the line of the hole. And this was a model study, of course. In the follow-up of the semester, we were then interested in the question. Somehow this now illustrates the whole working process, workflow we apply since then in our teaching. If you have found out a mechanism or mechanism, spatial architectural rules in an abstract space or in a model space, the next step is to pose the questions: how could this work, or how could we produce this in real scale with real materials, and what the consequences of these things are? Is it feasible, and what changes? Here you see, if you wanted to produce this in concrete, in a heavy material, to dissolve completely a concrete wall of this thing, the first thing you have to do is to produce a formwork that contains this information. So the formwork was drilled. In the two parts of the formwork, you could introduce plastic tubes, and this whole thing would produce a very complex formwork. Here you see the formwork. It could then be used as a mold and produce kind of compressed strings. Produce those artifacts. And here you have the first now impression of what we understand, or what we started to define as digital materiality. So you have a material you are familiar with that suddenly, just by being manipulated in a certain way, starts to contain or to transmit or talk about, not on an intellectual level. It's very physical. It's about seeing and not seeing, about relationships, about light. Starts to contain logics that we were used to operate with and to know in computer space throughout the 90s. Not just as programming architects, trying to bring together those things, but those aesthetics, you find them on renderings, because there it's very simple, for example, to apply some textures and manipulate images, but you are not used to finding them in your real 3D, touchable, tangible environment. This is very intriguing to us, and led us to further experiments we will show now. We're now going to start basically the couple of projects and research that we did on additive fabrication. Now, what we call additive fabrication is very simply basically adding elements, aggregate material to a larger whole. And why we think it is important to architecture, well, basically you have to look around you. You realize that 99.9% of architecture is actually produced by the addition of building elements and the composition of building elements and the junction of building elements to start to enclose and define space or exterior relationships. It's simply because by taking away material like milling, subtracting material, this is just a too uneconomic process for architecture. So interesting enough, after all the research which has been done in the 90s already with digital fabrication, the additive logics were not really a large subject matter. So there was one, the main reasons why we also chose the robot as a building instrument, because it was open so that we as architects could define our procedures. Now to start with additive fabrication, we decided to use the brick, because the brick is maybe kind of the oldest additive building element. There's about 9,000 years of documented history. And here you see one of our students, actually now a member of our team, building a brick wall by hand. Why is it important to kind of build something by hand? It's exactly by the manual process that you start to learn about the physical constraints of, in this case, this defined building element, what you can do and what you can't do. So basically what the mason does, you also have to learn it and to start to appreciate it in order to understand the rules behind it, and then to be able to formulate it in a more kind of, I want to say abstract, it's actually very concrete, in a more concrete way, in a computer program. Because building a brick wall is very similar to actually a computer program, as I said in the introduction, basically defining a sequence of steps which then end up in a built wall. Here it's two loops nested within each other, one for the row and one for the height. Then in the meantime, while the students were designing their program, by literally programming, although they didn't have any programming skills, that was not so important here, it was more the logics which were important, we had to teach the robot how to actually handle stone. So we kind of, based on a industrial gripper, we added parts so that it could actually first movements are a bit clumsy, but the bricks are glued by hand. And here you see these first three walls. It was very interesting to us, and we were glad, because it was kind of proof of concept that it matters to bring those two things together, is that we had not seen brick walls like these before. So by the simple fact that although all these walls, they could theoretically be built manually, it simply would not make any sense to build them manually, unless you had it as an artistic concept. But otherwise, in a kind of architectural economics, it only makes sense to do this, and there's this word selbstverständlich in German. We don't know how to translate it, but it's like making sense, basically. It's very self-verständlich to build a wall like this with a robot, where actually the positioning of each individual element can be different and very precise without any further effort. And to make this by hand would not make any sense. So, kind of the architectural expression starts to change. What is very interesting also is that the material quality can be appreciated more than what we were used to when we think of brick walls. I don't know how you apply it here mainly, but in Switzerland most brick walls are basically flat walls which are pre-produced panels and put in front of the building, so the brick is a mere kind of memory of what a brick building was, which has some positive affections as a material, but the actual kind of material quality, like here for example the reaction on different rotations of the light, we actually kind of lost these qualities, and suddenly through digital processes we we refined kind of these qualities. In another project, the resolution wall project, we said, okay, a human can lift a brick of roughly 1 kilogram of weight for a consecutive number of hours, and the robot can lift 110 kilograms for 24 hours a day. So what would actually the brick look like for a robotic process? We were not so interested in that kind of engineering question, but rather were interested in the question of resolution. What if we had different brick sizes, in this case volumetric kind of pixels, the largest being 40 by 40 by 40 centimeters and the smallest being 5 by 5 by 5 centimeters? What would this question of volumetric resolution mean to architecture? This, of course, implies, again, an economic question, because building the same wall of 7 by 4 meters with the large blocks takes you 9 minutes of building time. Building the same wall with the smallest stones takes you 80 hours. So the economics comes back in. So we expect a kind of negotiation between the economics and the design intent. Here's the building, it's a porous concrete block. Here's a changed gripper. Maybe the experts see that it's different from the last one. So we have to start to change the hand in order to do different processes. This one kind of sticks in this porous concrete and then pulls it apart to hold the block. You see, video is played very badly, but you don't know. What's interesting with additive processes is that you can actually assess the interior of materials. You see here very nicely. So the depth of the material is open during the construction process. So it's open to either inlay different materials, start to integrate voids or different materials or situations with different properties. And that is very schematic. And here you see the results. What's interesting to us here is that suddenly we find, so kind of following these questions of research, we start to find new aesthetics, which this is one extreme example. Foam project might be another extreme example, which come out of this research, and so it's very inspiring to us to actually start to look at these and learn from these kind of physical artifacts, and also ask the reverse question: what could they actually do for us? I'm not going to go into the project details because this would take too much time, but of course if you look at such aggregations, you could also think of the value of such kind of spatial logics and elements in other scales. So that triggers a whole lot of possibilities. I would like to show you a project we just did recently. It was a kind of a very fast project, but kind of maybe to quickly share with you, it's basically a furniture a company which has a website, a platform for furniture. They go to all these furniture fairs and present themselves there. The company is called Architectonic, and our basic concept was actually taking on this kind of question of this additive aesthetic. So the concept was actually to produce cubes which could be used as kind of backdrop elements, table elements for discussions and computers which were set up there, and seating elements. So this is kind of basic concept draft, all within cubic boundary shapes, which would then be eroded and additively produced. So it's a kind of play between the logic of kind of a subtractive aesthetic and an additive aesthetic. these were produced in foam, and the way basically the design was produced was basically this kind of what you've seen, this blow up of a virtual form within the envelope, which produced, once you quantize it in these voxel shapes they were built from, which produce these kind of elements. So this is the smallest piece for sitting on, the next larger piece as a kind of potential table project, and the largest pieces. The smallest piece has been at the least erosion, because this is where you need the most mass so that you're still able to sit on these foam elements. The middle piece had more erosion, and the largest piece had most erosion, also out of an economic logic, because you can imagine it takes quite a lot of foam to actually fill up a large volume. So then these elements, it would have been nice to have this all kind of computer evaluated. We actually within the time didn't get there, so it was human evaluated but computer generated. We produced quite a lot of instances of these shapes and evaluated these for the kind of criteria that we needed them to have. For example, we looked here, the green elements, you see these are elements which are not buildable, because we built up these elements from ground up, and since we built them with elements of different lengths, we could do a certain level of cantilever, and certain would not work. So we had an analysis of these, and then some evaluation which ones we would then actually choose and build, and which ones not. Here we show you quickly how this build-up looks like. So through the layering, what is really interesting here, we can achieve these kind of cantilevers, which brings up the theme, which maybe in the foam project we're going to further elaborate, of the actually construction procedure, which is kind of interesting conceptual theme here. Here you see these elements. This is the large one. It is kind of freely combinable objects, and the aesthetic kind of revolving, coming out of this. So, next project is called the sequential wall. It's a further development of this additive process. It works with wood slabs. Basically, the main difference to the brick is that wood comes as a two-dimensionally in the section as a defined geometry or material. The third dimension can be very easily manipulated throughout the process. So it gives you a further degree of freedom in a very simple and somehow easy way to be integrated into a process. Here we see first the concept models of the students. That shows again that what we've seen in all the projects right now, our approach is in the beginning very physical, because we believe that this comes from our own experience. If you start to design or to design in computer space or through programming, the risk that you somehow underestimate some very important constraints of physical space, of material, is high. Even things you would think everybody knows, like gravity or problems in the sequence of montage, of putting together things, it can play a very important role. Can for example, decide if something is feasible or not, if something is expensive or not, and it can, in our opinion, even drive a design. So lead to aesthetic qualities can only be experienced in real space. I mean, for example, a brick in the computer, you can put the brick in the air, it doesn't fall down, it stays there. Then you can take the next one and put it underneath and build the wall the other way around. In physical space, this doesn't work. I will not elaborate on all the projects because I think we have to speed up a bit the lecture. I'll just show you again examples of built products. It's always the same format. It's the wall of this studio. What is special here is that you see it on the next one here, is that even though those projects have so each one of them has a very simple big logic in the beginning. So it's built in section or from bottom to top. They start to address, you see it there in the section, to address more complex architectural issues. This wall, for example, it's not just I mean structural stable, but it creates holes or voids in the section that allows for thermal insulation. They could put insulation in it, and with this strategy of cantilevering out of the wall, it exploits or it creates kind of a constructive waterproofing. So the main function of this overlapping needles somehow is to take humidity, water away from the facade. So very classical or archaic construction systems that apply into this very sophisticated variable design element. Here you see the back side. You see this very nice connection between the inside and the outside. Same element. On the one side, it becomes very expressive and very functional too. On the other side, it just draws in a very subtle way the movement without having any volumetric or plastic dimension. Same applies to this second project here. Back side. Here you see this special in this project is the level of detailing. So how do you put things together? Can you still nail them? Do you have the overlapping you need or not? Such structure are very easily done in computer, because there the computer is very tolerant. Things do not fall apart if the joints do not work. Yeah, on the one hand, this is the simple thing. On the other side, in the computer model, if you strip something like this, you will never have such, I mean, the beauty of such details in physical space, because they are just not relevant. This was the follow-up of this studio where we set up the question: how can you put openings or make openings in such structure, because we felt that an opening should come out of the logic of the wall itself. So you should kind of start with the opening, or the system that allows an opening, and transition to closed part, and not the other way around. Because if you have a system that does not consider this, the only way to make an opening is to cut out an opening. That would somehow be in conflict with the additive logic that should allow to do this. Again, they're stretched, I think. Okay, now the last additive project or research studio project we would like to show is kind of the extreme example for additive fabrication. It's kind of the other, if we say on one side we have this brick thing. The brick is something everybody knows, very familiar, cheap, simple to build. Foam is the inverse. Foam is a high-tech material. The brick is solid, so you can take in your hand. You just have to connect brick somehow. Here you have just liquid, a liquid that turns into solid, and by solidifying, it expands. So it augments its volume, its mass. The process is very simple. We have our robot arm, and instead of a gripper, we put this nozzle on the hand, and we allow the robot to move around in space and to deposit material. And this is the the panel we have seen after maybe 5 minutes when the process is completed. Now, why did I show you the video? Of course, it's interesting and funny to see the movement of the robot, but we are convinced that this particular one was very important, and it somehow illustrates this gap between those two images. On the left side, you have the geometry designed by the students. It's a very simple, a little bit variated grid. Basically, it could be a perfectly regular grid, wouldn't matter so much. And on the right side screen, you have the physical artifacts. And of course, you will notice that these two images do not have a direct relationship. Of course, if you know that they are related, you can tell that there must be something. But even if you wouldn't have seen the video, the process of making, you would not understand what the relationship is. And the main quality of this of the video is that it's showing process in time, showing something I cannot document with images. And it's illustrating, and this is the conceptual point that interests us a lot, it's showing in a dramatic way that design or the making of material artifacts is not just a geometrical issue. Or let's say geometry is a part, maybe an important part depending on the process, but just one aspect. The other much more important aspects, at least in this particular setup, are time and sequence. So what comes in which sequence in place. And this thing is true even in the simple construction process. As I said before, a brick wall too has a very precise sequence, so from bottom up, and that cannot be reversed. Of course, in a brick wall, the formal consequences of the sequence are not so visible and not so dramatic, but I mean, they decide, for example, if something is buildable or not. Now here, those consequences are extreme, because if I deposit a line of foam, now depending on, I deposit a line, then I do something, and I come back and I cross with the second line the first line. Depending on how much time passes between those two moments, so the first deposition and the second deposition, I get a completely different result. You have to imagine if I proceed quickly and I'm back to the material, say 5-10 seconds later, the two materials are liquid, so they melt together, and the crossing or the knot that this produces is homogeneous. If I return to this point and cross the first line 30 seconds later, the first one has already expanded. So the ground, the building ground has changed. It's physical properties in the meanwhile, and the liquid falls down or on the two sides of the three-dimensional first line. What causes or generates such very interesting shapes? Here I show further examples, the same principles of other designs, always the geometry and the results. We talked a lot at the crits of this study about the aesthetic of this thing, but to us in the moment the most important and interesting kind of result is this it's the fact that there are processes that, or where the control of the process itself, of the sequence, determines in such a dramatic way, or radical way, the result, and that the result is not, and this is another particularity of this thing, the result could not be produced differently. So those shapes you cannot mill them, you cannot cast them. It's physically impossible. And third thing that is very interesting, those panels here are reproducible, technically reproducible. So if I run the same process again, what is very difficult, of course, because temperature, humidity, everything influences this foam. But if you run it on the same condition, you will get the same result. Even though this looks completely random, it is not random. It's all determined by a process that is designed by our architects. can be manipulated. Here are just two images. This was a follow-up semester. Was trying was the try to go or to build higher structures as audio acoustic elements. So those are were designed to be acoustic panels for acoustic diffusion. So we needed a certain depth of structure. I would like to start to move the scale a bit towards an architectural one with the winery Gantenbein project. It's an extension to an existing winery. You see the new building here on your right-hand side. The building was conceived by Beat de Plates architects, and Andrea de Plates, being the dean of DTH, he was at our final crit of the studio of the programmed wall, which I showed you before. And although the building was basically already built to its socle, he was asking, well, can we use this technique for this winery extension? We were confident in doing so, although this required, from an initial conceptual prototype to a building, this required quite some adaptation. So we said yes, we would be willing to take up this theme and design the facade of the building. The requirement for the facade, here you see the outside, was that it was supposed to be an open structure. They intended to actually use bricks put on their side so that through the holes where you put your fingers in to place the bricks, actually diffuse light would come into the space. The idea is that in the inside it's a daylit space, but there is no direct sunlight which would destroy kind of the grapes ripening in this hall. So I would quickly like to show you how we did the design of this facade. This was also generated synthetically. We looked at the building, which was kind of a given situation to us as a basket, and we interpreted this basket as one to be filled with abstracted berries here of three sides of these spheres, and these sides, they were kind of adapted to the resolution, which was in fact the brick that we had to start to imprint this facade. So we looked at this kind of virtual container and filled it, packed it digitally, and then looked at this basket from the four facade sides and transferred this view into the basket on the rotation of the individual stones. So it is a mixture between this kind of three-dimensional illusion of the inside and the two-dimensional facade. What we like is, on one side, we have this image quality of this building facade, but when we come closer, we actually start to lose this kind of pictorial quality and come to the individual rotation of the stones and to this very dynamic surface, although basically these are flat panels with just rotated stones. So we like the aspects that the kind of material quality can be rediscovered through these processes, and that multiple visions of one same instance can appear. You see view from the inside. For the inside, it was, for example, very important to realize that the stones had to be moved very closely together, so that when you rotate the stones, the actual gap between the stones would start to close. Only if that closures would actually appear, you would actually see something of the pattern in the inside. If you would only have moved all the stones slightly apart and rotated them, in the counterlight you would actually not have seen anything. That's one point where we see that the actual kind of physical research is as important as the digital one when you want to actually merge these two subjects. And I mean, this is kind of the architectural side of it, but we would also like to share kind of the making of it, because I think this is extremely important in this context. Working on this project. There's not eventuality, but he does nice. So we teach the robot how to move the stone, and as each of the stones is individually rotated, all the gluing parts on each stone is also adapted to the rotation of the stone below. It's something which is very easy to calculate, but which you might not very easy to do, because you would have to anticipate the next stone. This is the part which is not industrialized, it's the feeding of the... And it's maybe important to say that we are not interested in automation and all these subject matters, but we only build the parts which we think are relevant in order to achieve a certain goal. Then there are other people that are much better in very nicely here is how the wall looks different from different perspectives, different angles, or different distance. The project was realized within 4 months from the initial idea to the completion of the facade. Sorry about that. The Cerruti Pavilion is a competition which we did in 2007 for art galleries in Paris. Maybe you've seen other competition results. And we were interested in actually taking some research results and actually making a pavilion building structure with what we already knew we could do at the moment. So here you see a site plan on the site which belonged to André Bloch sculpture, and he built. I'm going to show this right away. On the right hand, on the upper side, you see his house which he built. And then you see two kind of weird-looking structures, so-called habitacles. It's actually brick structures, hand-built, very amazing sculptures. And on the lower part, you see our proposition for the pavilion. This is a view of the site. You see this marvelous small house, one of the habitacles, and then from the upper part of the site, this fantastic view from Meudon towards the La Défense, the city of Paris. These are these habitacles, actually very fascinating handmade structures which would probably need some research to be understood how they are actually made. Very fascinating parts. And this one especially was standing right in front of our pavilion. So we decided to actually join our building in the corner of the party wall to the adjacent neighbor properties, and to have the building completely horizontal as opposed to the vertical habitacle tower. So it was a one-story pavilion structure with load-bearing brick walls in the inside, forming a core structure which you see here, and composing kind of a back for opening views on the sides, on the views which I just shown you on the top, and kind of towards this existing wall, which were more kind of the intimate chambers. So here you see the kind of layout of this structure. All the services were concentrated in the core. And we adapted the brick wall system so that it would be closed where when the bricks were not rotated. Usually the wall, if you have a regular brick structure, the wall would be open when the bricks are flat and closed visually when the bricks are rotated, because the brick becomes longer in projection. So here we would do the reverse, which would then result in a kind of shifting brick structure, which would be again a reference to the more chaotic manually built brick structure of the habitacle. This would be an outside view of the pavilion, and here you see some inside views of this proposed pavilion building. What was interesting to us, and we actually always work from there, is that we think, or this pavilion could have been built more or less right away. If you would have had Rob at that moment, it could even have been built on site. So here we see the inside in the model. We also did the roof structure with these kind of tilted holes, with the idea to actually give sight to the habitacle, but also to allow lighting at different moments of the day of the several activities which were happening within the core. Here you see the top of that roof structure. It was planned to be a concrete roof. And you see the inside. The roof was slightly hanging within this core to articulate the interiority of this space. You see the complete project. Okay. This is the last project. Somehow this is kind of sort of synthesis of the project we have seen so far. It's the installation at last year's Architectural Biennale in Venice. We're invited to be part of the exhibition in the Swiss Pavilion, and we decided to kind of provide the infrastructure to the pavilion. So to produce a wall, 100-meter long wall that would articulate the spaces in order to generate different parts of the spaces for the different players in this exhibition. What you see here is the line. It was the first step. The second step was we did not, this is shown in this image, we did not design the wall or the shape of the wall or the surface of the wall, but we did design a kind of behavior or a set of rules that would inform the physical properties of the wall. This for two reasons. The first reason was that the setup was very complex, four-parting, showing their research work, their studio work, and so on. And as everybody that's done exhibition knows, this is a long process back and forth. Maybe I want more space here, and we changed this. And we said, in the end, we don't really care a lot about where this line goes through. We will not. First of all, we will not be able to control this till the end, and we are much more interested in designing, creating a robust system that would allow to be used as we call this kind of line of negotiation between us, the curator, and all the parties involved. In a way that if somebody comes and changes, picks the line there and puts it 3 meters away, the design, the overall design, the product would not suffer under this manipulation. On the other side, and this is what you see here, we set up very, I would say, very strong rules that could not be easily aggressed or put into discussion or in this process, because they are very basic. What you see here is where the line is straight, here in the configuration, the wall will start to undulate. It will undulate on the floor and have a counter undulation on top. This for a very simple reason is for the reason that this wall is produced in elements. This wall is very thin, just 1 brick thin, and if you want such an element to be stable, because in the pavilion you have no foundation, you cannot drill down the elements or something. You have to put them inside, and you have to make sure, you have to be sure that people could not, even in panic, tear them down. So it's a constructive strategy where the line goes around or makes a curve, you have no need for this, so you keep it straight. This is the basic principle. So we were not obliged for us anymore to design those curves, those shapes, but we, or the system was generating them by itself for the actual configuration. So if we moved the line to another place, it recalculated everything and made sure that the structure was working. Here you see these elements that were then produced in place, 4 meters long. And here you see a rod that was built by a contractor that is a research partner of ours for the Biennale, for Venice, but also for the production of industrial production of the elements we have seen. ROB is basically the same machine we have at ETH, but it's built in a container, what allows to bring the machine in a very cost-effective, simple way, not in the construction site, because there you have security issues and things like this, but nearby the construction site would allow you allows you to produce elements just in time. You do not have complex and expensive transport of complex elements. Of course, Venice is a very, very bad place to test such a system, because you have a breach in a couple of steps every 50 meters in direction. Okay. This is ROB when the roof is opened. You can just start to work in front of it. We have a short movie illustrating this process. So here we see, compared with our setup at ETH, this is a real sophisticated industrial setup now that can be used. Here you see an interesting side issue. If you produce a wall that is, it's again about the process. If you produce a wall that is not vertical, you will have moments, for example, before the glue having starting to hold the whole thing together, or in some geometrical configuration when the upper part is not in place, giving counterweight, you will need construction helping to hold together the whole thing. There we just used bricks that were not glued, that afterwards could be reintegrated in the process. Now, those are images of the pavilion. Here you see the construction is paper thin. This would never work without this geometrical manipulation of the surface. Okay, so I maybe would like to draw a couple of very simple last conclusions to this presentation, then open up the discussion. I would like to maybe to say that all these projects show that we are, or kind of demonstrate that we are really convinced that in order to exploit digital means of design, of controlling data, of programming, of scripting, you have to engage with the counterparts, with the physical counterparts of this process. And that this is not just about knowing how machines work or which machine does what, but it's about a more fundamental investigation of the possibilities of digital fabrication. It's about conceiving processes, it's about testing them, and it's about kind of reintegrating those findings in the design process itself, not as limitation or constraint, but as a driver to design. And we are convinced that this is right now a fundamental issue, because those technologies do not exist yet. But they will exist in 5 to 10 years. And the very important question is, will we as architects be part of the definition of this product, of this strategies, or not? So we are convinced that as architects we have, or we will gain if we engage with it, an enormous degree of freedom. We will finally give all these digital strategies we are playing around since 15 years now a real architectural scope and sense. So we'll solve this conflict Matthias was describing in the beginning. So the digital world on one side, accessible, pieces are everywhere, we can program and so on, we can produce images, and the missing link on the other side with the construction industry that is still conservative, that still limits you to a couple of very simple processes. Basically, I would say through industrialization, the architectural culture has stepped back to the design of shape in the first step, and in the choosing of choosing of materials out of a catalog. And with machines that we can control, we can get back a freedom that we have lost, the freedom to really go into the details of making things. And we think that now it's the moment we can step into this process. We think we are legitimate and we have the tools. Because if we do not do this, the same thing that happened with software throughout the last 15 years will happen again. The tragedy with software is that we as architects completely ignore the issue. Not everybody, but the majority, the industry of architecture. 15 years ago, 80% of architects said that they will never need or use or apply some CAD software in their office. And 15 years later, everybody is obliged to use them. Not because they are good, but because they are fast. But this software is not coming from a confrontation between our needs, the needs of our industry, but it's coming from engineering, and it's just sold to us. And if you compare this attitude with the attitude of another industry, film industry, in the 90s, that basically, and this happened here, basically reinvented itself. I think that Pixar and Toy Story reinvented itself through the direct engagement with the possibility of a new media. You can somehow feel what the potential of an engagement now with digital fabrication could be to architecture in the long term. Okay, I'd like to thank you very much for your attention.